All right, on to multivariate miscellany, and we're going to be talking about lecture 11.1, dimension reduction applications, and this is a continuation of the module on multivariate models. No required readings, but I will point out the paper that the data and code were taken, some of the code was taken from for this lecture, in case you want to follow up on the very interesting results they found, which will be slightly different than what I show you. Okay, so we have talked in depth about how multivariate ordination can be a great way to reduce dimension for multivariate correlated data, but we have not yet put into practice this idea. So we're going to focus on how to reduce dimensions and then test hypotheses with those reduced dimensions. We will start by creating a reduced dimension X variable. We'll be focusing on this paper by Groves, Bauer, and Brodvig, and they're looking at grassland restorations and how a restoration site's age and weather in the planting year influence its total cover of desirable species, which are prairie species, the ones that were sown that we want, and the non-desirable species, and these are mostly weeds. So the data. Here's just a subset of the data, and it's looking at each row is a site, a restoration site that they sampled, and you have the site's age since 2016, and then its biomass, and then a bunch of weather variables in the year that the site was planted. And so to reduce the climate dimension, right, because we have 11 climate variables in the data set, and it's, a lot of them are correlated, and so it doesn't really make sense to try to put 11 variables in your X variables in your model. We can reduce the dimension with PCA. So, and this also applies for PCOA or NMDS as well, but we're going to be focusing on PCA here because that's what they did in the paper. So we can use the PRComp function with your restoration, which is the data set, and the columns that relate 4 through 14, which relate to the weather. And don't forget, you want to center and scale those variables. And then here's the summary of all 11 PC axes. And what we see is that PC1 explains 39% of the variance, and PC2 explains 22% of the variance. So that's pretty good for the first two axes. So we'll be focusing on those two. And so if we want to try to understand which what variables are really explaining or sort of falling along PC1 and PC2, we can plot them here or print them out here, and then we look at the absolute value of each variable on each PC. And so for the first PC, the highest absolute values tend to be related to degree day. So anything with a DD, that tends to be correlating with PC1, and so that's more of a temperature variable on PC1, and then PC2 tends to be correlating more with precipitation variables. So when you look at the absolute value of the PC correlations for PC2, you see that the ones with the highest values, absolute values, tend to be related to precipitation. So let's pull out a value for each plot for both PC1 and PC2. So we're going to pull out our columns 1 and 2, right? And you can see here that there's one row for each row in the data set, so each site that they studied for restoration. And so we can just, because we know that those two data sets, the PC data set and of climate and the restoration data set, are in the same order, we can just C-bind them. And then we have, here's just a glimpse of some of the data set, and you can see again we have our restoration site, its age, its biomass, and then again some of the climate variables, and then all the way at the end we have the two weather PC axes. And so let's run some linear models. Let's look at how this all works. So let's look at how the average cover of sown species, or your desirable native ones, are a function of a restoration's age and the climate variables in the year that it was planted. So here we'll look at the log of the cover, the mean sown cover in a linear model as a function of age since 2016, plus PC1 and PC2. And then we're going to look at this output with a capital ANOVA. And again, remember you use type 3 because this you don't want to assume order here. And here you see actually that none of our variables are significantly predicting the cover of our prairie species, which is very interesting. However, when we look at how the average cover of our non-zone species, or our weedy ones, are a function of our restoration's age and the climate variables, we actually see that the year since the restoration was planted, the age of a restoration actually significantly predicts the cover of the non-zone or weedy species. And I will point out here that our two PC axes of reduced dimension are not predicting the cover of the non-zone species. And so what Groves et al. Decided they would try was, instead of taking their PC1 and 2 values, their PC1 value, which was a continuous variable, they thought maybe they should make it categorical. I thought this was a pretty neat trick and some nice code, so I wanted to include this here. So they thought, what happens if you make your PC1 variable categorical based on how different years are from the average. So we will make an average category where the climate variable on PC1 is 0.75 standard deviations away from the average climate for PC1. And then we'll make a warmest category for all values above this range, and coolest category for all values below this range. And so here's just some nice code to do that. You can investigate that on your own, but you can see the resulting data set has a column for each site, its age, and the two PC axes that we have previously collected, but then also the group categories. So warmest, average, and coolest. And so when we look at our average cover of our non-zone species, again, as a function of restoration age and the climate variables, and the categorical ones this time, we see that again, looking at the log of the mean non-zone cover as a function of age plus the group, which is the PC1 category, we actually do not see a significant effect of that category still, but we do see an effect of age. So what does this look like? Here's a graph looking at restoration age on the x-axis, and the log of the mean non-zone cover per meter squared on the y. And normally I wouldn't recommend that you color the lines by group since the groups were not significant, but I just wanted to point out here that this is what it would look like. And so, right, what we found was significant was age of the prairie, and so as the restoration age increases, you see that the cover of the weeds actually increase. And so I just wanted to keep these climate groups in here because in the paper they do a little bit more in-depth statistics and they actually find the three to be different, but they do a more in-depth model than what I'm showing here. So I just wanted to, in case you go back to the paper and see that they found something different than us, I just wanted to point that out. Okay, and so you can also do the same thing for your response variables or your Y variables. So say instead of wanting to look at plant cover, you want to look at how restoration age and climate affect the soil properties of each site. So now your new Y variable is going to be your soil properties. And here is looking at the data, in that data set, there's a lot of soil properties for each site. So a huge range from pH to organic matter to phosphorus, calcium, etc. So there's a lot of soil variables that you could also look at. And so again, we can reduce our dimension for our soil variables using PCA as before. And when you look at the summary, here are the 18 PCs for the soil variables. And you can see that PC1 explains 40% of the variation, so we're going to use that one for our Y. So we'll be representing our Y matrix with that single PC axis. And so you can again pull out your soil PCs. Here I pulled out soil PC1 and 2, but we're only going to use soil PC1 in the model. bind it to your data set, and then run a linear model where you're looking at soil PC1 as a function of your prairie age, plus PC1 for weather and PC2 for weather. Again, using your capital ANOVA with type 3. And here we see that age of a prairie does not affect its soil properties, but the weather PCs actually do. They significantly predict what the soil is going to look like. And so with that, please complete the quiz 11.1 on Canvas and continue on to the next lecture.